Dear students, let us resume back to our video lectures on machine learning for image processing. Let us continue our discussion with the regression. More specifically, let us discuss about logistic regression. So in the previous class, we have seen how minimizing the mean square error cost function is equivalent to maximizing the likelihood of P of y given x for the regression problem. Now in this lecture, let us continue our discussion in understanding how the regression framework, which is used to estimate or predict or find out, map the continuous variable from the input features, can also be applied in the context of classification. The technique that we are referring to is discussed as logistic regression. As we have seen in the regression, the estimate of yk is obtained as W transpose xk, right? And these W's are found as solution of regression, and hence referred to as regression parameters. Okay, so in mean square error based minimization, what we have done is R square error based minimization. We have found out the norm of yk hat minus yk whole square, or in essence yk minus W transpose xk, which is yk hat, is minimized with respect to W to find out the parameters W star or W. Okay, in probabilistic framework, P of yk given xk we have constructed, and which is nothing but a Gaussian with mean W transpose xk, okay, and the variance sigma square, same variance as epsilon k, and this we maximized with respect to W and then found out W star. Both yields we have seen that they both gives the same solution, which is Wt plus 1 is equal to Wt minus eta times W transpose xk minus yk into xk. W transpose xk minus yk into xk. Right? This is for a single sample. They update with single sample xk. Xk is a random sample. Then what we do is the weight update equation by gradient descent. Stochastic gradient descent provides us the weight update as this, as solution to regression problem. Parameters, right? As we discussed there, what yk is a continuous variable or real number. Okay, so essentially what we are doing, we are estimating yk hat as some parametric form, okay, of xk, wherein hw of xk is here is W transpose xk. This is fine to map a set of features to a continuous variable, because the W are also real, right? This yields a real number. However, in classification problems, if you want to bring in a similar framework as that of the regression, we need to map this W transpose HW xk to be mapped to class 1 or class 2 labels. That is 0 or 1. Okay, if we wish to apply for a binary classification problem, the mapping of this HW should rather be mapping to a binary value 0 or 1 rather than mapping onto a real number for classification. Right? So now the question is, this is for regression. For regression, we can directly consider whatever we have here, right? So now the question is, if we want to bring in this to 0 to 1 range, what is a simple operation on HW? How should we modify HW of xk such that still it is proportional to W transpose xk? That is, it is still parameterized with W, but we want to have it in 0 or 1. So we should bring this value to probabilistic friend. See, now to bring this to a probabilistic value, there is a function that enables us to range any of the real variable to 0 to 1 range. So can you recollect the function which will map any real variable to a 0 to 1 range? The function that we have seen before is sigmoid activation function. Sigmoid function. So now let us see if we want to redefine HW of xk as through sigmoid function such that it maps from 0 to 1. What we do is 1 by 1 plus e power minus W transpose xk. Given this, now you can see that if W transpose xk is high, tends to infinity, imply that this HW of xk tends to 1. Whereas if on the other case, HW of xk, if W transpose xk tends to minus infinity, that's the other side of the real line, then HW of xk approaches to 0. So these two enable us mapping the real variable W transpose xk, whichever we used for conventional regression, to a classification problem, mapping the W transpose xk to 0 to 1 line. And hence this can be considered in constructing the class probabilities. Or classification probabilities. So now what we want to construct is the probability function for yk, in the sense that, say, yk, if it is a class, if you want to pose this as a classification problem, y hat k will tend to 1, is assigned as 1 if HWXK is close to 1, right? And y hat k is assigned as 0 if HWXK tends to 0, right? However, we can formulate, based on this, we can directly formulate as a label yk. This is the label and this is the estimate. Okay, this is written in terms of HW. That's all. So the actual label is 1 or 0, right? So we can directly formulate this as a mean square error problem, mean square error minimization. For classification. This is one way of doing it. The other way of performing it is to construct a P of yk itself we want to construct. Given xk, because xk we assume that it is given. We want to construct given the background that we have. As we have seen, probability that yk is equal to 1 given xk is given by what? Is given by HWXK. This is because, as we have seen here, what does this indicate? this simply indicates that this infers that probability that yk is equal to 1 given xk is directly can be taken from hwxk, in the sense that the probability is 1 if hwxk is high, right? That is 1. And if the yk will not, the probability that yk equal to 1 is 0 if hwxk itself is 0, right? So from this we can directly write that p of yk given xk is equal to hwxk. To write the complete probability of p of yk given xk, since yk takes two values, 1 or 0, we need the other term as well here. That is, probability that yk is equal to 0 given xk also has to be noted. How much is this? How should we write this? If this is hwxk, the probability that yk equal to 0 given xk will be 1 minus hw of xk, right? So this is 0 to 1, and this gives probability of yk equal to 1. This gives the probability of yk equal to 0, right? Given these two, now the probability of yk given xk can be written. How do I write? See, if I consider as a yk as one variable, it can take both 0 or 1, right? Whenever it takes 1, I should get hwxk, right, as the output. Whenever it takes 0, whenever yk takes 0, I should get 1 minus hwxk. So the probabilistic function p of yk given xk should be a combination of hwxk and 1 minus hwxk. And whenever yk takes 1, it has to come. This first term has to be active, or it has to be there. Whenever yk takes 0, the second term has to be there. So we can write it as yk into this one plus 1 minus yk into this one. That is one way of writing. The other way is yk hwxk power yk into 1 minus hwxk minus 1 minus yk. What does this do? This also makes us to express p of yk given xk in terms of a unique expression for, and it naturally dissolves to whatever we have defined here. This is exactly expressed in single expression, right? And this is more convenient because this we can consider it as likelihood of yk given xk. And what do we want to do in the classification problem? If yk has to take 1, we maximize the likelihood of yk. Okay, so we pose this as a maximizing the likelihood probability of yk, right? So the problem is posed as maximized with respect to w p of yk given xk. So let us continue our discussion in looking at the solution to this maximization problem.